Welcome to the 6th video in our Quantum Computers series. Previously, we covered quantum computing basics, designed our first quantum circuit, and encoded it on Qiskit and Google Circ. Check out the updated version on qubit-lab's website, which includes videos, Python code for Google Colab, and more resources. In the first deep dive video, we introduced matrices and explored quantum gates, learning their prerequisites and capabilities with Python examples. Then, in the second deep dive, we had a look at complex numbers, phases of quantum amplitudes, and quantum interference. Today, we will conclude the deep dive level by investigating multi-qubit systems and entanglement. There is also a supporting Python notebook again for this video, which you can open in Google Colab. Just press the button below the video on the qubit-lab.ch webpage and the Python notebook starts in a new browser window, ready to be used and modified by you. Okay, let's go. In the previous videos, we used quantum gates that operate on one qubit only, single qubit gates, like the Pauli gates X, Y, and Z, and the Hadamard gate. As those gates do not interlink qubits, they keep every qubit separate, there is no entanglement possible using them. But this is not the end. Besides single qubit gates, there are also quantum gates that act on two qubits. That means they have two input and two output qubits. Due to the unitarity requirement for quantum gates, as seen in video 4, we always need the same number of inputs as outputs. Let's look at a common example. The CNOT gate is a typical 2-qubit gate. CNOT stands for controlled NOT. As the NOT gate is the Pauli X gate, this gate is also known as the CX gate. What does it do? One qubit connected to the CNOT is the control qubit, and the other one is the target qubit. If the control qubit is 1, then the X gate will be applied on the target qubit. If the control qubit is 0, then the target qubit stays unchanged. There are two notations in quantum circuits for the CNOT. The circled plus and the dot, or the X gate connected by a dot to the control qubit. It is the same gate. There is also a CY and a CZ version of the Y and the Z gate. Same logic. If the control qubit is 0, nothing happens. If the control qubit is 1, the gate is applied on the target qubit. Now let's look at the whole circuit. Qubit 0 will go through the Hadamard gate and end up in a superposition state, the plus state, as we learned in video 4. Qubit 1 is initiated as 0. Then, going through the CNOT gate, it will switch to 1 if qubit 0 is 1, or stay on 0 if the control qubit is 0. As we have a superposition in qubit 0, both options are true simultaneously. The target qubit is in state 0 as well as in sum 1. A superposition, same as qubit 0. As long as we do not measure any qubit, both qubits are in a balanced superposition. But the two qubits are not independent. They are interlinked. If one qubit is measured, it will be 0 or 1, randomly at a 50-50 chance. In this very moment, the second qubit will also decide on 0 or 1. Due to the logic of the circuit, it must be the same outcome as for the first qubit. If qubit 1 is measured 1, the second will immediately also fall into state 1 and stay there. If it is measured 0, the other qubit's state will also collapse to 0. As said before, the CNOT gate is also known as the CX gate, a controlled X gate. In a quantum circuit, it can be shown as a plus sign in a little circle or an X gate box connected to another qubit, the control qubit as shown here. Both notations are describing the same setup, no difference. As mentioned before, there are also controlled Z gates. They are shown as a Z-gate box with a connector above or below. Looking at the situation after the CNOT gate, we have two qubits which are both in a balanced superposition, but they are not independent. If one is measured, it will behave normally and take a value of 0 or 1. But the second will immediately also flip to the measured value of the first one. They are linked to each other, miraculously. It does not make a difference whether you first measure qubit 1 or 2, the outcome will always be the same. The remaining qubit will match the first measurement outcome, always. We say the qubits are entangled. Entanglement is the third and final exotic phenomenon of qubits, following superposition and quantum interference. Let's take a closer look. As you should not just take everything I say for granted, you should test it in Qiskit. This video, and some of the others on qubit-lab as well, come with a Python notebook. This notebook contains various code snippets that encode and execute quantum circuits or calculate quantum gates. You can explore the Qiskit code hands-on, run it, change it, or save your own copy to come back to later. And the best part, no setup required. Just click the button below the video and it opens right in Google Colab. Your browser handles everything. Super simple. Give it a go. Best viewed on a notebook or a desktop. We start with a simple circuit, something like a four-sided die. 2 qubits, each going through a Hadamard and then measured. When you execute this using Qiskit, you will find that each qubit in superposition will show 1 or 0 at about a 50-50 chance. As both qubits are measured and they are independent of each other, all possible outcomes for the two measurements 0, 0, 1, 0, 0, 1, or 1, 1 do have the same probability. This is evident if you execute the circuit 10,000 times and count how often each combined state appears. In the notebook you find the Qiskit code for this. To the right is the result. All 4 possible combinations are equal. Now we go to code byte 2. We encode the CNOT setup from earlier and do the same as above. The result is quite different from the one above. Only states 0, 0 and 1, 1 are measured. No measurements for 1, 0 or 0, 1. That shows that the 2 qubits were entangled. So what do we learn from that? It is not meaningful to investigate a single qubit's state vector if it is entangled with another one. A single qubit state vector cannot encode entanglement with another qubit. We must see the entangled qubits as a system, so we introduce a new basis of 4 possible system states. 0, 0, 0, 1, 1, 0, and 1, 1. Having now 4 basis states instead of 2, as for single qubits, we also need a new state vector for a 2-qubit system with 4 probability amplitudes, 1 for each possible basis state. And finally, in order to apply quantum gates on the new 4-state vector, we need to expand quantum gates to 4x4 matrices instead of 2x2 ones for single qubits. As a quick in-between exercise, I let you explore the below circuit. But before you execute the Qiskit code in the notebook, think about it and predict the outcome. Stop the video here and do it. It will be fun. We start the journey here with a quick refresher. As long as we do not interlink qubits, we can use single qubit state vectors with 2 probability amplitudes for the 0 and 1 state. The quantum gates working on single qubits are 2x2 matrices. So far, so good. If we connect two qubits in a circuit, we need to expand the basis to 4 possible states. 0, 0, 0, 1, 1, 0, and 1, 1. As said, this leads to 4 state vectors and 4x4 matrices for the gates. Let's continue the journey. If we cross-link 3 qubits using CNOTs or other 2-qubit gates, or if we use a Toffoli gate, for instance, which requires 3 input qubits and 3 output qubits, then we need to expand the base even further. Now we have 3 qubits, each can be 0 or 1. That leads to 8 basis states, 2 to the power of 3. These basis states are 0, 0, 0, 0, 0, 1, 0, 1, 0, and so on. You get the picture. Any state vector in a 3-qubit system has therefore 8 probability amplitudes, and the matrices we need to calculate it are 8x8 matrices. Now, if we want to describe a system within qubits, we get 2 to the power of n basis states and must work with 2 to the power of n by 2 to the power of n matrices. Everything quickly becomes quite bulky. One might also ask, if quantum computers can crack the RSA encryption so easily, and quantum computers are also not really fast in calculating, can't we simulate quantum computers using classical computers and get fast results? The idea is generally good. It is called quantum-inspired computing, but it aims more at certain general approaches, not on emulating production-grade quantum computers. The reason is simple. To crack the RSA 2048 encryption, it is estimated to need at least 4,000 qubits. The Shor algorithm interlinks these qubits heavily. If we need to fully emulate such an algorithm, we would need to calculate with matrices of 2 to the power of 4,000 by 2 to the power of 4,000. This is insanely big. Maybe you heard that the number of all atoms in the observable universe is estimated to be around 2 to the power of 256. So quantum computers can do great things, but classical computers do not have the capacity to really simulate more than a few dozen qubits at best, using some tricks like isolating qubit groups not interlinked, possibly some more. But there seems no way around physical hardware. Let's build on what we learned about single qubits in video 4 and extend it to a 2-qubit system. The general state of a qubit is the sum of the 4 basis states, each one multiplied by its respective probability amplitude. The state vector of a 2-qubit system is a 4-vector of those amplitudes. When measuring a 2-qubit system, the system can only fall into one of these 4 basis states. You get the probability to measure each basis state by the Born rule. The squared absolute value of the respective probability amplitude is the probability to measure the basis state. And our reality check transforms to the condition that the sum of all 4 probabilities must be 1 or 100%, as there are no other possibilities around. Same logic as before for single qubits, but now we have 4 instead of 2 possible measurement outcomes. Now we look at how we can calculate the required 4 state vectors from the single qubit vectors. We return to the initial CNOT sequence and start with both qubits in the 0 state. After passing the Hadamard gate, the first qubit is now in the plus state. The second qubit is still in the initial 0 state. As the 2-qubit states now approach the CNOT gate, a 4x4 matrix, we need to transform the two 2x2 vectors into a 4 vector that can interact with the 4x4 matrix of the CNOT gate. This is done using the tensor product. If we take the tensor product of the qubit 0 state vector and the qubit 1 state vector, we get the required 4 state vector. We won't prove this here, we will just use it. The rules for how to calculate it are shown below. Normally we don't do this kind of thing by hand. Instead we use NumPy in Python. The tensor product is also known as the Kronecker product. If you import NumPy as NP, you'll find the function under the name np.cron. I've added more examples in the notebook. Check out CodeByte4 for instance. Alright, now that we have the 4-state vector, we multiply it by the 4x4 CNOT matrix to get the final vector. The result is a 2-qubit state, 1 over square root of 2 times the basis state 0, 0 plus 1, 1. This is what's called a Bell state, and it represents a maximally entangled 2-qubit system. Let's look at the same circuit again. This time we want to calculate the overall matrix for the sequence of gates. First we use a trick to transform the first 2x2 gate into a 4x4 matrix. As the second qubit is not going through a gate when the first one passes the Hadamard, we assume an identity gate below the Hadamard. The identity matrix does not change the state vector as intended. Now we can do the same as for the vectors. We use the tensor product. The tensor product of the Hadamard and the identity gate results in the shown interim 4x4 matrix. Then we multiply the CNOT matrix with the calculated interim matrix and get the overall matrix for the sequence. In order to test this, we can multiply the found overall matrix with the initial 0, 0 state vector and we get the same Bell state as before. So it worked. In the CodeByte4, we will calculate the setup we just examined. In CodeByte5, you will encode a 3-qubit system with a Toffoli gate. Before you look at the Qiskit code in the notebook and execute it, think about it. What might be the result and why? The code will deliver the answer. So, what's next? You've now completed the foundational and deep dive levels of qubit-lab. Congratulations. That's a big step. You now understand superposition, interference, and entanglement, the exotic core phenomena of quantum computing. But quantum computing isn't just theory. In the upcoming videos, we'll shift gears and look at how quantum computing is applied in the real world. We'll explore how quantum algorithms are designed to solve real problems, why finance, chemistry, and AI are considered key early application areas, and how famous algorithms like Shor's for factoring, Grover's for search, or VQE for molecule simulations actually work. We might also look at hybrid algorithms, combinations of quantum and classical techniques that are already being tested today. And don't worry, everything will stay hands-on and practical with Python code and ready-to-run notebooks. So stay curious. Quantum computing is just getting started. Visit qubit-lab.ch for all videos, code, and resources. And if you liked this video, tell others or just leave a comment. I'd love to hear what you're working on. Thanks for watching. See you in the next video. Have a great day.